This is question 10 from the third CSAT sample paper. In this question we're told there are n circles in a plane. Each pair of circles intersect twice, and we're asked to find the minimum and maximum number of disjoint closed regions we can make. So let's just clarify what this means, disjoint closed regions. Disjoint means the regions don't overlap. So suppose we just have two circles, then we count three regions, 1, 2 and 3. So for instance, if you took this sort of crescent here and this crescent here and called them and sort of thought the combined region, you can't count that as a separate region because it overlaps with what I've already called 1 and 3. So they mean just these individual regions 1, 2 and 3, not any combination of those. And what does closed mean? It basically means they're of finite size and they have edges. So if we just have one circle, for instance, that's one region. It's not the inside region and the outside region. The outside region doesn't count because it's not closed. Hopefully what they mean by this should just be sort of intuitive from the picture, that if we have the circles overlapping, we just count these small regions inside as shown. Okay, so with that in mind, if you want to have a go at this question yourself, pause the video now. Okay, so there's a couple of things we have to think about. One is we've got to think what makes for a minimum case versus a maximum case. And the other is we've got to actually count those, and this is in general in terms of n, so it's likely there's going to be some kind of recursive formula that we'll discover. So first let's think about what makes for having more or fewer closed regions. So something you can do here is just play around with circles, trying to make as many regions as you can or as few as you can. So let's look at the extreme cases. So how can we make as many regions as possible or as few as possible? So if you make as many as possible, it's like making a Venn diagram. So here's with just three circles. What we try to do is to spread them out evenly so each overlaps with each of the others as many times as possible. So you should know from having done Venn diagrams with three circles, this gives you 7 regions as shown. So that in a way is easy, making as many as possible. It might take a bit more experimenting to get as few as possible. So here's a kind of picture where you have fewer circles than you might have if it was a Venn diagram type shape. Here I've drawn 3 circles again, so there's this one, and then this bigger one. But now there's only 5 regions. So you can see I've deliberately lined them up so that they I don't have as many intersecting regions as here. But we need to have a methodology behind this. So how did I know to draw this instead of this? Well, since we're doing this for any n, it helps to think about what happens when you add one circle to a shape you've already got. So suppose I add a circle and that means it intersects some of the others, and that means I'm adding extra vertices. And every time I add an extra vertex, I'm adding an edge. So suppose I just had these 2 circles and then I added this third large one. Then that means I added, well, it intersects these 2 circles at these points. That means I add an edge here between those 2 points, and I add an edge here between those 2 points. If we look at this case, suppose I just added this circle, and it intersects here and here, so I add this arc between those 2 points. It intersects here and here, so I add this arc between those 2 points. And then here and here, so I add this arc between those, here and here, so I add this arc. And we can think about saying, well, I added this vertex. This vertex is sort of on the right hand end of this arc, and this vertex is on the right hand end of this arc, and likewise every new arc has a vertex at the right hand side, so for every vertex I add I get one more edge. And you can think of it as instead I added this vertex, and that means I've split what was one edge before into 2, so I've got an extra edge, and that's going to split a region I already had. So you can always sort of count in 2 different ways. And when you add an extra edge, that means you add an extra region because it splits a region in 2. So this case is easier because there's fewer edges. When I added this edge, it split what was one region into what are now 2 and 3. When I added this outside edge, it split the outside region which wasn't counted into another outside region that still isn't counted and an inside region. So every edge, whether it's on the inside or the outside, adds one more region. So that means if I want to maximize the number of regions, I want to maximize the number of vertices and edges, and if I want to minimize the number of regions, I want to minimize the number of vertices and edges. So we're talking about maximizing or minimizing the number of vertices. How can we do that? Well, if we look at these two pictures, what's the difference? In this case, I deliberately made all the circles intersect at 2 points only. So I'm not adding as many new vertices when I add a new circle. I'm just adding one here and one here, whereas when I add a new circle here, it has to intersect here, 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 and here, so 4 times. Okay, with that in mind, let's look at the minimum case and try to count how many regions there are going to be. Okay, so in the minimum case, we said we're minimizing the number of distinct vertices. And let's think about what that looks like each time. If we have just one circle, there's no intersections. If we have 2, they have to intersect like this. If we have 3, we already said we're aiming to have them intersect again in the same place. So can you see how I'd add a 4th circle to keep doing the same thing? Well, I want it to intersect at these 2 points again. So that means I'm going to want an arc in here, which means I'm going to need a larger radius of circle because the arc has to be more shallow in order to fit in here and not cross this again. And that means it's going to be large around here, and that's fine because then that adds me an extra region on the outside. So you can see if I add the 4th circle, I just add it like this. And then suppose I want to go up to 5, I'm not going to draw it because it starts getting difficult to draw. But you can imagine if I zoom in, I can make an even bigger circle, so this arc is very flat and then it goes way out here. And then once I've drawn that, I can imagine zooming in again, so when I zoom in again, the arcs that looked flat before, I can see more of the curve, and I can imagine adding an even flatter one. So I can just keep adding circles like this. So basically this pattern can be repeated no matter what the value of n is. So we're saying we can just keep adding larger and larger circles to the right, and we just follow this pattern. And each one, we split a region in 2, so what was region 3 here is now 3 and 4 here. What was region 2 here is now 2 and 3 here. And it adds an extra one to the right, so we added this region here, and then this region here, and then this region here. So we're adding 2 regions each time. And that means the formula shouldn't be too difficult. So we start off with just one region when there's one circle. And then we add 2. So I'm writing R1 for the number of regions when n is 1, R2 for the number of regions when n is 2, etc. So here is 1, here is 1 plus 2 is 3, then I'm going to add 2 again. So 3 plus 2 is 5. So you can see this is an arithmetic progression with common difference 2. So if this continues, what's the formula for n? We start off with 1, and then we add n minus 1 lots of 2. And then if we multiply this out, we get 2n minus 2 plus 1 is just 2n minus 1. And so that's going to be our value for the minimum in terms of n, the minimum number of regions we can make. So now let's think about the maximum instead. Okay, so for the maximum we want to maximize the number of vertices, remember, which means we want 2 distinct intersections between every circle and every other circle. So we want to try to picture how that happens. So one thing to note here is if we have 2 circles and they're within a space that's less than 2 diameters wide, then they have to intersect twice if they don't overlap. So if they were exactly, if I fit them in a space exactly 2 diameters long, then they can touch at this middle point, because you've got 1 diameter here, 1 here. If I make it more than 2 diameters, then they cannot intersect. But if they're squished within 2 diameters, then they have to intersect. There's just not enough space for them not to. And that pattern will carry on if I have multiple circles as well. So here's a case where I've got 4 circles, and if I make sure each of them is, so the outer edge is within 1 diameter of this central point, then only 2 of them are going to be within 2 diameters, and they're going to have to intersect twice. And then in order to stop those intersections being the same, I just use symmetry, so I arrange them symmetrically around the center. So let's explain what we're doing. So we can always get two distinct intersections with every other circle if they're spread symmetrically around a central point at less than one diameter from it. Because, as we said before, two circles within two diameters always intersect twice. And the symmetry means that those intersections aren't the same. Okay, great. So we can always continue this pattern. We can always get exactly two intersections with every other circle. And we were saying before that for each new intersection we get one new arc and we get one new region. So let's go through the values of n. So if we start with n equals 1, we just have one circle again, and the number of regions is 1. And now I've drawn these 2 points down because this is where I'm going to attach my next circle. So if n equals 2, we've seen this already, we just attach the circle there. And we've added 2 new arcs because of our 2 intersections, here and here. And each of those divides a region in 2, so we have 2 more regions. So now we've got 3. If we imagine going up to 3, now we have added 4 intersections because the new circle we've added, this one, intersects twice with each of the other circles. So that's 2 times 2 new arcs, and again each of those introduces a new region. So now we started with 3 here and we've added 4 now, so we get 7. So we can see what the pattern is going to be because here we added 2 more arcs because it intersected twice with 1 circle. Here we added 4 more arcs because it intersected twice with 2 circles. The next time it's going to intersect twice with each of 3 circles, so it's going to add 6 more arcs. So each time we're basically adding 2 times n minus 1. So where there's 3 circles, we're adding 2 times 2 because there were 2 before. And when there's 4 circles, we're going to add 2 times 3 because there were 3 circles before and a new circle intersects each of them twice. So we've got this recurrence relationship. The number of regions for n is equal to the number of regions for n minus 1 plus 2 times n minus 1. So now we just have to work out a non-recursive expression for this. Okay, so here's the relationship we're starting with. And how do we unrecursify this? Well, imagine starting with 1. We know we start with 1 and then we add 2 times 1, and then we add 2 times 2, and then we add 2 times 3, etc. So let's just write that. We start with our 1, and we add 2 times 1 plus 2 times 2, etc. all the way up to 2 times n minus 1, and this is the last term we add. And now we want to rearrange this. So our 1 we know is 1, and then we can take out a factor of 2 from all of these, and what's left is 1 plus 2 plus 3, etc. all the way up to n minus 1. And you should know a formula for the sum of the first k integers. That's a half times k plus 1. Here is the first n minus 1 integer, so that's a half times n minus 1 times n. And we're timesing that by 2. So if we simplify this, the 2 and the half cancel, and then we just have n times n minus 1, that's n squared minus n plus 1. So this all comes to n squared minus n plus 1. And that's going to be our formula for the maximum. So we were advised in the question to check this, so let's do that quickly. So we're going to check this formula for the maximum. So here I've drawn circles with 2, 3 and figures with 2, 3 and 4 circles. And let's see, in the case where there's 2 circles, we've obviously got 3 regions, I'm not going to label them. And then we stick in n equals 2 in here, we get 4 minus 2 plus 1, that's 3, so okay, that works. In the case where we have 3 circles, we can number these 1, and then 2, 3, 4, and then 5, 6, 7. So you can see the symmetry helps you count. And we want to stick in 3 into here and get 7, but that's fine because we get 9 minus 3 is 6 plus 1 is 7. So that's correct. And then when there's 4 circles, okay, so we have to count. There's 1 region in the middle, and then 2, 3, 4, 5, and then 6, 7, 8, 9, and then 10, 11, 12, 13. So here, if you'd seen the way to get this symmetrical pattern, then you could also have just noticed the pattern in how you can count the regions. So 1 in the middle, and then in this case 3 lots of 4, in this case it was 2 lots of 3, so it looks like it's going to be n minus 1 lots of n. and that gives you the same formula as this. So you could do that just by sort of observing this visual pattern as well. But in any case, let's just check our answer. So we can see we counted up to 13 here, and if we stick in n equals 4, we get 60, and the minus 4 is 12, plus 1 is 13. So that's correct as well. So that's probably enough checking. It looks like our formula is correct. So therefore we can write down our answers. The maximum is n squared minus n plus 1. The minimum is 2n minus 1. If you wanted to, you could check this is always greater than or equal to this for positive integers. So it's equal when n is 1 or 2, and then otherwise this is bigger than this.